Okay, good evening, everyone. How are you tonight? Beautiful, beautiful evening, and welcome to Carnegie Science's Earth and Planets Laboratory and our first edition of the 2025 Neighborhood Lecture Series. It is my great pleasure. I'm Mike Walter. I'm the director at EPL, and it's my great pleasure to introduce our special guest speaker tonight, Carnegie President, Dr. John Mulchaey. John has been a Carnegie scientist for 30 years, maybe a bit over 30 years. It was a postdoc at Carnegie before that, so spent most of his career here. For the past 10 years, he has held the Crawford Greenwalt Chair in Astronomy and was the director of the observatories in Pasadena and director of the telescopes in Las Campanas in Chile. He also, during the past 5 years or so, has held a role as the deputy for science at Carnegie and twice was interim president. So he's well-seasoned leader here at Carnegie. We're very, very fortunate to have him as our new president since November. John, as a scientist, has really developed his renown in the field in his work on understanding galaxy groups and galaxy clusters. We'll hear about some of that tonight. He led a team that discovered or revealed the existence of massive amounts of dark matter, this enigmatic material that we still don't really know what it is in these galaxy groups. Earlier on in his career, he was part of an international team that discovered the first binary quasars. And these are really amazing objects. I'm not going to do a spoiler, but I think we're going to see a little bit about that here later as well. John's been like I said, in Pasadena for the past 3 decades, but he's no stranger to this area. He also got his PhD right up the street at University of Maryland. So we're very fortunate to have John back here tonight. John is also a prolific ambassador for science. He gives dozens of lectures, public lectures, every year. It's a very important role these days, I would say. He started what is sort of the West Coast version of the Neighborhood Lecture Series called the Astronomy Lecture Series at the Huntington Library. And if you're interested in attending some of those, you can get on our website, find out when they are, and it's 2,662 miles away, according to Google Maps. But you'll be welcome. So this year, we celebrated the centennial anniversary of Edwin Hubble's, Carnegie scientist Edwin Hubble's discovery of a galaxy outside of our own galaxy. It is amazing to me that was only 100 years ago, that we didn't realize that some of these objects, which we called, I guess, maybe nebula at the time, were actually outside of our galaxy. And then a few years later, Hubble discovered that the universe was expanding, and that kind of set up what are now is sort of the modern cosmology. We understand that there was likely a big bang, and that's the beginning of sort of the previous golden age, maybe, of astronomy. And tonight we're going to hear about the new golden age of astronomy, Hubble's universe today. So, John, welcome, and thank you.
All right, thank you, Mike. All righty, thank you everybody for coming. I'm excited to be here. Many of you know that this was originally going to happen in January, and then unfortunately we had the fires in Pasadena, and so I had to cancel. The fires got very close to our very historic campus where Edwin Hubble did his work, but thankfully our campus did fine. It also got within about 20 feet of our very historic, I'm going to show some pictures of Mount Wilson Observatory where Hubble did his work, but that also survived, so that's the good news here. But the reason I was planning to give this lecture in January was because January really was the 100-year anniversary of the announcement of the discovery. I like to call it the discovery of the universe. As Mike said, it's the discovery of other galaxies, but effectively that took us from understanding that we lived in a single collection of stars to the immense thing we think of today. So in my mind, Edwin Hubble discovered the universe, and that was announced in January 1925. It was, by the way, announced in Washington, D.C., which is why we wanted to do the talk here. So we're a couple months late, but still it's about 100 years, so that's pretty good. We won't complain about that. I should say I'm going to talk about modern astronomy and some of the things we've learned in the 100 years since Edwin Hubble, but I like to start with history. I always like to start with history. We have a lot of history at Carnegie, of course, but I want to start even going further back because it's really quite interesting. The idea that there might be other galaxies actually goes back several centuries. The first person that is known to do this is a man named Thomas Wright, who came up with really quite a brilliant observation. He saw that the Milky Way wrapped around the sky, and he understood that this could mean that we were basically embedded in a disk of stars, which is effectively true. And that meant that maybe that's why we see it wrap around us. And he went a step further and said, maybe there are other systems like this out there. Really quite brilliant. And these results were picked up by Kant a few years after that, and were known as kind of island universes, which is a term that became very popular. But really, Thomas Wright was the first to suggest this way back in 1750. I think it's pretty remarkable. This is a drawing of the first, what we call spiral nebula. This was an image taken with this rather spectacular, this is a reconstruction, it's not the original telescope, but you can see this. This is in Ireland, which is, by the way, not a great place for a telescope. You can imagine you want clear skies and good weather. But this was, William Parsons was an amateur astronomer, really not very much of an amateur. 72-inch telescope is really quite impressive. But he used this telescope and looked at a lot of fuzzy things on the sky. And this is one he drew in particular called the Whirlpool Galaxy. There's an image from the Hubble Space Telescope there in his drawing. You can see he did a really great job. And so this was kind of the first time these things called spiral nebulae had been seen. And of course, this is ultimately what Hubble ended up finding. And of course, you live in one of these called the Milky Way. But this was pretty remarkable. Now, you would think, even though the idea that there could be other universes out there would have taken hold, in fact, you just saw an image of one of those things, and maybe that idea would have spread. But as is often the case, sometimes the biggest minds of the time are often stuck in their ways, I would say, and prevented progress. And in this case, it was two very, very famous astronomers here who actually pushed back against this island universe idea. And the reason for that is because they saw other sorts of nebula on the sky. Here's 4 examples here of things that were known as nebula, or nebulae. This is Orion, this is the Ring, this is the Crab, and that's a spiral galaxy. These are 4 vastly different objects. The first 3 are objects in the Milky Way. The last one is an external system. But through a small telescope, these all look like blurry, fuzzy things. And so they assumed all of these things were kind of the same. And they figured all of these things had to do with places where new stars were being born. So those things at the end had to be star systems that were forming. And so the island universe idea kind of died out, even though there was pretty good evidence it could have existed. And it died out until really the early 1900s with a man named Curtis, very famous astronomer from Santa Cruz. He worked at Lick Observatory, one of the other early observatories. And Curtis made a really brilliant observation. He was taking some images and realized there were some edge-on systems that looked like this. And he made a connection between that and the Milky Way. He saw the Milky Way in the sky and said, oh, this dust lane in the Milky Way must be one of these things edge-on, kind of going back to that idea from Wright. And so Curtis became convinced that these spirals were in fact external systems. Okay, now we get to where Carnegie gets involved, or Carnegie scientists. One of our very famous astronomers, Harlow Shapley. Now, so Curtis at Santa Cruz believed these island universes were external systems. Harlow Shapley, in 1918, did the first measurement up at Mount Wilson, which is our Carnegie's facility above Pasadena, of the Milky Way. And what he did is he did a measurement, an estimate of the size of the Milky Way. What he did is he studied star clusters, particularly globular star clusters, looked at the distribution of them, and he came up with one really important result. What he realized is the distribution was skewed on the sky. What that meant was that we were not at the center of the Milky Way. Now, I'm pointing this out because up until 1918, humans believed we were still the center of the Milky Way, which was effectively the center of the universe. Some people still think they're the center of the universe. But 1918, that was a big result. But the other result he found was that the Milky Way was huge, according to his estimate, so large, in fact, that he was convinced those other things couldn't possibly be up beyond the Milky Way. So Harlow Shapley believed that those spiral galaxies were actually in the galaxy. And this led to what is known as the Great Debate back in 1920 between Harlow Shapley, who suggested the universe was only the Milky Way, and Curtis, it's kind of blocked there, who suggested there were island universes were galaxies. And so it turned out this great debate of those very famous in astronomy wasn't a debate at all. That's because Shapley didn't talk about spiral nebula at all. He decided he would just talk about the size of the Milky Way, and he kind of gave up there. And Curtis did talk about the spiral nebulae, but there wasn't really a debate. They each kind of did their own statement, and that was it. And in fact, Harlow Shapley might have been the Edwin Hubble of the world if he didn't make one fatal mistake, and that he made that mistake right around 1920. He left Carnegie to go be, it's true, he left Carnegie to go be the director at Harvard University. Now you can't, the observatory, you can't blame him. That's a very prestigious job. But what that meant was he left behind the world's biggest telescope in the world, which was just being built by Carnegie astronomers above Pasadena. And so a young man took advantage of that in the fall of 1919, and this is Edwin Hubble, who came from Chicago. This is a picture of Hubble. You always see Hubble in a complete suit. He was a very serious individual. He had worked at Yerkes Observatory in Chicago. He came to Mount Wilson, and he now had access to the biggest telescope in the world. And he basically took over when Shapley left the study of these spiral nebulae. This is the telescope. So this is the 100-inch telescope at Mount Wilson. I argue this is probably the most important telescope ever built. You could also say Galileo's telescope might be the most important build, or this one. One of these I would argue. This is the telescope the universe was discovered on. That's pretty significant. I'm a little biased. It happens to be a Carnegie-owned telescope, but it's still pretty important. Anyhow, this telescope came online in 1917, but it took a few years for it to get going. And so, but by the time Hubble arrived, it was ready to go. What was important is this telescope was so much bigger than any others that you could study individual stars in these spiral nebulae. And that was not possible before. So Edwin Hubble decided to do this. He was very interested in a special type of star called a nova. A nova is a system. We now know these are binary systems like this with a white dwarf and another bigger star, massive star. Material from the massive star falls onto the white dwarf. It kind of has an explosive event, gets very, very bright, and then fades. The thing about these nova is they get bright and they fade, often weeks, months, years. It takes a long time, very long time scale. So Edwin Hubble decided to look for nova in some of these spiral nebulae. And this is the first image he took on October 5th, 1923, of what was then known as the Andromeda Nebula. It's not a particularly good image. The conditions were rather poor. But to find the nebula, you have to take an image one night and then an image the next night and see if these things got bright, if something happened. And in fact, they did. And this is the image the next night. And in fact, you see he had some things labeled N. There's 3 of them. One of them is crossed out. That's a key one. And the end are the things he identified as nebula. Now, why did he cross one out and cross out and put VAR? VAR stands for variable. Because what he did is he took an image a couple nights later and realized that that star had gotten bright, faint, and then bright again. And the nova don't do that. The nova get bright and then fade for weeks or months and then maybe get bright. This star had gotten bright, faint, bright over a very short time period. He had a different type of star, and this is called a Cepheid variable star. Cepheid variable stars are special because their variation allows us to determine the distance to them. It's just that there's a relationship between those parameters. You see the exclamation point on the VAR? Hubble knew when he found this star that he could measure the distance to this object. And when he did, he found that the system was much, much further away than anybody had realized. So he spent the next few months studying Andromeda, kept taking more data. He found many more of these. And finally, in February 1924, he had enough data to show that this was that kind of star and that he found other of these variable stars. And he had measured the distance to Andromeda. And Hubble was, Hubble was quite a character. By this point, he had become kind of a, I wouldn't say Shapley, I would say was his, not nemesis is a strong word, but I would say his competitor. And so he wrote to Shapley, who at this point had been at Harvard for a few years, and with this great statement, and dear Shapley, you will be interested to hear that I have found a Cepheid variable in the Andromeda Nebula. He went on to inform Shapley that the calculated distance to Andromeda was around 1 million light years away. So he instantaneously showed that this was much further away than anybody realized. And there's this famous Shapley response to a colleague, here is the letter that has destroyed my universe. And so, in fact, Hubble had discovered the universe and Shapley was wrong. Ironically, Shapley was the one that went on to name these things galaxies. Hubble didn't like that term, but Shapley still get credit for it. Anyhow, this was where it was announced, January 1st, 1925, right here in Washington, D.C. These are some great old things from the newspapers. I love some of this. If you read these, they're really quite interesting. It's worth looking these up at some point. I won't go through them in detail, but you can see where they talk about how the universe has gone from this small thing to this immense thing now. Now, as Mike mentioned, that was Hubble's first big result. This was 1925 when this came out. 4 years later on, he went to find that not only was the universe bigger than people realized, but that it was expanding. And this is the result that people talk about. I actually think discovering the universe is more important than discovering that it's expanding, but discovering that it's expanding is pretty important. And what he did is he just found a relationship. What he found is that objects further away from us, the galaxies further away, are moving away from us faster than the near ones. And this relationship is due to the fact that the space between the objects is growing. And so an object that's further away, there's more space to expand. And so it appears to be moving faster than us. And so this basically showed the expanding universe. I should point out that Hubble himself did not ever say the universe was expanding. He didn't like to interpret the data, but Einstein and many others, of course, did. And of course, it was true. And as Mike said, if you think about this, tracing this back in time, it meant the universe was smaller. And this is a key element of the Big Bang. So we'll talk about, I have to show this famous picture from our library in Pasadena. This is, of course, Albert Einstein. Very famous picture taken on February 5th, 1931. Albert Einstein made one big mistake in his career. He had assumed in his models of the universe that the universe was static. That is, the universe did not change in size. But now Edwin Hubble had just shown in 1929 the universe is expanding. Einstein admitted that that he was wrong in our library on February 5th, 1931. So this is a really key figure. Anyhow, we like to point that out. But he's not exactly wrong, but we'll get to that later. He thought he was wrong, but he did mean the universe isn't static. That was wrong. Okay, so now I want to talk about some modern things. So what have we learned about these galaxies since Edwin Hubble's discovery 100 years ago? So first of all, let me just take, this is a beautiful image of a spiral galaxy. If you could zoom out and look back at the Milky Way, this is what our home would look like. What are you seeing here? You're seeing the light of about 200 billion stars. So in the case of the Milky Way, the sun is just one of those 200 billion stars. Really quite remarkable. And here's the distance across here. It's about 100,000 light years, which means absolutely nothing. I put it in miles. That means absolutely nothing either. These numbers are so incredibly large, they can't possibly be understood or comprehended. But when you see an image with a telescope, what we're really seeing is the stars. But of course, the stars are not the whole picture. We know there's lots of stars there, but what else is there? Well, of course, we now know that there are probably planets around most of those stars. And that's an area where people in this campus have really concentrated a lot. We have a lot of expertise here. We call these systems exoplanets, that is, planets around stars other than the sun. As of today, there are 5,862 exoplanets known. I had to look that number up. It's pretty good. It's almost 6,000 exoplanets. And the interesting thing, this is a drawing which shows you approximately where almost all those exoplanets are known in a very, very tiny region around us. I mean, we just don't have the techniques to see them very far out. But if you look at that area and you estimate, well, what's the average number of exoplanets a system probably has, and you assume you have 5 per star, which seems to be an okay average. That means if you have 200 billion stars in a galaxy, and each of them has 5 planets, that would mean you would have about 1 trillion planets. It's a huge number, right? You live on one of those trillion planets in the Milky Way. When people often ask me about life in the universe, I'm like, there's 1 trillion in the Milky Way, probably. Even if it's off by a factor of 10, it's still a huge number, right? I mean, the universe is immense, and this is one galaxy, which we'll talk about later. What else is there? Well, the one thing you definitely don't see, but we know is there, was also done on this campus, and this is, of course, the very famous result from Vera Rubin and Kent Ford. Kent Ford helped build the instruments that Vera used. She should have gotten the Nobel Prize for this work. This was a real mistake on their part not to give it to her. What you might know, and of course, this is that the universe, galaxies are dominated by dark matter. This is this mysterious thing that Mike mentioned earlier. And about 90% of the stuff in the galaxy appears to be this dark matter. And so what did Vera find? Well, you would naturally expect that in the solar system, as you go out in the solar system, the planets move slower as they get farther from the sun. That's because all the mass in the solar system is at the center. And so the gravity is strongest at the center. In the galaxy, that doesn't happen. You see this observed plot. As you go further and further out in the galaxy, the stars keep moving at that high speed. This means there's a lot of mass in the outer parts of the galaxy that we're not seeing. And this is the conclusion she came to in 1970. A really very important result that we are still, as Mike mentioned, trying to understand what it is. I'll talk a little bit about that later. But let's add that in. So a galaxy, 200 billion stars, 1 trillion planets, 90% of it is we don't even see, and that's the dark matter. We also know of the last 20 or 25 years or so that pretty much every big galaxy has at its center of what we call a supermassive black hole. A black hole is just an object that has such strong gravity that nothing, including light, can escape it. What do I mean by supermassive? I mean something maybe 1,000,000 to 1,000,000,000 times the mass of the sun. Pretty massive. So how do we know that there's black holes are there? We can't see them. Well, we know for a couple reasons. One is that even though you don't see the black hole itself, we can see the material around the black hole heating up. As this material swirls in towards the black hole, it produces what we call an accretion disk. And this material heats up by friction and emits light. And so we can see the light around the black hole. And in fact, these were first discovered in the 60s in Pasadena by Caltech and Carnegie astronomers. This was the first one found. This is called a quasar. You see the very, very bright point there. It turns out that's in the middle of a galaxy. The point is so bright in this image, you don't even see the rest of the galaxy. But that bright point is actually the emission from right around the black hole. And in this case, it's about, once again, 1,000,000,000 times the mass of the sun is our estimate. This is one of my favorite images or animations in all of astronomy. This is another way we know about a black hole, and this is really super interesting. What are we seeing here? This is a zoom in of the very, very center of the Milky Way galaxy. And the little white star, it will play again, is the very center of the galaxy. What you are watching is a time sequence over about 25 years of individual stars orbiting around the center of the Milky Way galaxy. And if you watch those stars, watch the one on the, let's see what's a good one. Maybe the yellow orbit, I think, is a good one. I think it's S02. Yes, it comes down. Watch as it comes down. Watch any of them come down. You'll notice what happens when they get near that center. They whip around really rapidly. This tells you that there's a very strong gravitational source right at the center. But if I took away that white star, there's nothing there. There's no light source. This is a black hole. And based on these motions, you can calculate the mass of that black hole. And in this case, it's about 1,000,000 times the mass of the sun. This is a pretty small supermassive black hole. But this result by Andrea Ghez at UCLA won her the Nobel Prize. And the similar group in Germany won it for the same result. This is, in my mind, the most direct evidence for a black hole. Okay, so this is everything we have. 200 billion stars, trillion planets. Okay. I should point out that galaxies come in all different sizes and shapes. This is one of my favorite galaxies, the Sombrero Galaxy. You can see why it's called that. But I just want to point out, it's a pretty big galaxy, right? This is another galaxy. This galaxy is the same distance as the Sombrero Galaxy. And the reason I say that is because, of course, the size of an object could depend on how close it is. This is a difficulty we have in astronomy. But if two objects are at the same distance and they appear that different, that tells you that they're different in size. This is what we call an ultra-compact dwarf galaxy. I've studied this particular galaxy. That's why I put it up here. And it, in fact, is part of a system with this much bigger galaxy. Galaxies cover a huge range. A system like this does not have 200 billion stars like the Milky Way. It probably has maybe, in this particular system, something more like 10,000 stars. Really quite remarkable. So they come in all different sizes. They also come in a lot of shapes. So here I've been talking about spiral galaxies. We also have what are called elliptical galaxies. These are more kind of football-shaped galaxies. And we have things called irregulars. If you've ever been to the southern hemisphere and you've seen the large and small Magellanic Cloud, these beautiful things we see from Chile, those are irregular galaxies. They have no shape. That's why they're called irregular galaxies. And I should point out that Edwin Hubble's third result, which doesn't get as much attention anymore, is that he was the first person to kind of look at the different sizes and shapes of galaxies. And he came up with this classification scheme where he had these early elliptical galaxies, the football-shaped ones, and then kind of two different types of spirals. The two different types have to do whether they have what's called a bar in the middle. You can see the bar versus kind of coming in the middle. There was a long period where people thought that the galaxies maybe moved along this sequence and did that. You can move from one type to another with things happening, which I'll talk about in a minute. But for the most part, this isn't a sequence. This is just the different types of galaxies one sees. But you do get really interesting things that galaxies do. And so I wanted to show some of this. One of the things that will change a galaxy is if it merges or collides with another galaxy. These are just some spectacular images here. This one on the right is a relatively new James Webb image, so I wanted to include it. All of these systems are in the process of merging together. They're going to form, these are two galaxies that will merge and form a single galaxy. By the way, we won't, but our atoms will go through this process in about 5 billion years, because Andromeda and the Milky Way will do this in about 5 billion years. Now I want to show you I have a little simulation. This was a simulation a postdoc of mine did. So you see a galaxy, here's a second galaxy. This just kind of shows you how this works. So this was done by one of our former Carnegie fellows. So you can see how the first interaction, they kind of stream out. By the way, I don't know if you can see those numbers at the top. Those are billions of years. So it's about 1.2 billion years here. So at first that galaxy kind of goes up and it's going to escape, it thinks. Gravity will bring it back. And the second time it won't be so lucky. So here we come. And this time they get too close, and so they're going to basically come together. This was the binary quasar that Mike mentioned. That's why the image on the right I took from Chile. And I took this to my postdoc and said, can you model it? And he modeled it. But what he can do with the model is he can run it forward and see what happens, which I can't do with my data. And what you see is that eventually the galaxies will merge together to form a single galaxy. So this is kind of the future for the Milky Way. One thing worth pointing out is in this case, each of those galaxies has a supermassive black hole. We could see those, they're glowing. And so they will form together, they will merge together and form a much bigger supermassive black hole in this process. So this is probably how some of the biggest black holes in the universe are formed. Another really interesting thing that happens is galaxies can collide with galaxies. I just showed you that, but galaxies can collide with gas. And you may go, well, why would they collide with gas? Well, there are places in the universe with big reservoirs of gas, and these are often called clusters of galaxies, another area that I worked on quite a bit. This on the left shows you an image of visible light. So you're seeing the galaxies, the stars in the galaxies. Each of these kind of yellowish objects, they're all part of a single system. These galaxies are swirling around together in this giant system, which maybe has 10 to maybe 10,000 galaxies. These are the most massive systems in the universe. That's what it looks like in visible light. If you take an X-ray image of it with an X-ray telescope, it looks like that. Well, what is that? That looks like a big purple blob. What that's showing you is very, very hot gas, because hot gas emits a lot of X-rays. And why is the gas hot? It's hot because there's just a huge amount of gravity here, and gravity will heat that gas up. And so galaxies can interact with that hot gas, and that can change them as well. And here's a little simulation from another one of our postdocs, Stephanie Tonneson. Now this is, imagine a spiral galaxy falling into a hot gas, one of those clusters. You can see what's going to happen when it hits the cluster right there. And you can see the hot gas will actually strip the galaxy of all of its other gas. Basically, it kills off the galaxy in some sense. The galaxy stops forming stars, forms these beautiful tails. There it goes. And we see these. These are some spectacular examples. These are called, we call them jellyfish galaxies. Astronomers come up with really original names. This is one, so this one's falling in this direction. You can see this beautiful tail. This one's very spectacular Hubble Space Telescope image. So that one's, the cluster's up here, so it's falling in that direction. But you can see these beautiful tails are regions where the gas is being stripped from the interaction with that hot gas. This is a relatively new phenomenon. We really only recognize this pretty frequently in the last 20 or 30 years. But although we see individual galaxies that are undergoing mergers with each other or interacting with this gas, the real way to understand how galaxies have changed over time is to study them in the past and compare them to the more recent galaxies. And this is the way we do that. We go back to, this is Edwin Hubble, where we knew one galaxy in 1923 besides our Milky Way. But the Hubble Space Telescope has allowed us for the first time to really study the evolution of galaxies over time. This is, I'm going to show you my favorite image of all time. And this is called the Hubble Ultra Deep Field. Spend a minute on this. This is an image that was taken with the Hubble Space Telescope, pointed at a region of the sky for 23 days, integrating for 23 days, a very long time. The region on the sky corresponds to if you took a grain of sand and held it in your hand at about that distance. It's the tiniest little speck on the sky. When you integrate for such a long time, what you see are very, very faint things. This image, everything you see in this image is pretty much everything in this image is a galaxy. There are 3,000 galaxies in this image. The tiniest, why are they tiny? They're tiny because they're very, very far away. So the smallest ones in here are about 10 billion light years away. What does that mean? Well, because it takes time for that light to reach us from that distant part, we're really seeing these in the past. The example I often give is the sun is about 8 light minutes away. So when you see the sun, you're seeing the sun basically 8 minutes in the past because that light left the sun 8 minutes ago. In this image, you're seeing galaxies 10 billion years. That light has been traveling for 10 billion years. This is an image of the universe about 10 billion years ago. That's truly remarkable because I'll remind you the Earth is 4.6 something, where's my Earth scientist? 4.6, blah, 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 plus 4.6 billion years in the past. This is an image of the universe about 5 billion years before the Earth even existed. That's truly remarkable, right? So what we can do as astronomers is we can look at these old galaxies, see what they look like 10 billion years ago, compare that to the more recent ones like Andromeda and say how have they changed in time. And Hubble, this was a huge feat. Hubble's been up for over 30 years. In this image, that's the most distant thing Hubble ever found. This thing is found about almost 420 million years after the Big Bang. We're getting almost back to the Big Bang with Hubble. Really quite remarkable. But of course, Hubble has been blown away by the James Webb Space Telescope. So James Webb is about 3 times the size of Hubble. A bigger telescope allows you to collect more light and see fainter things. It also gives you sharper images. So this image with James Webb was done in 11 hours. And in 11 hours is already deeper than that previous one that took 23 days. It's remarkable. I'll show you some other ones. Oh, this is a great comparison. So here's a James Webb image and a Hubble image with basically the same exposure time. And you can just see how many more objects you see in the James Webb image. I like to do here's a comparison of a small piece of that. There's James Webb. There's Hubble. There's James Webb, Hubble. Point out a lot of things you see in this James Webb image. One, like this guy here, I don't know if you can see this, completely invisible in the Hubble image, just pops right out. There's another one here. You'll notice that those are very, very red. There's a reason for that. They're very, very distant for one, and they're very red. They're being redshifted because of the expansion of the universe. And James Webb sees infrared light. So their light is mostly in the infrared, and that's why they pop out as James Webb as well. But with James Webb, we're seeing about 5 times as many galaxies in the typical field than we could see with Hubble. It's really quite remarkable. And here's just some more spectacular James Webb images. I just want to point out that over the last year or so, I got blocked here, I think, but James Webb has found the most distant object 9 times. It keeps breaking its own record, about 9 times in the last year, or a little over a year. And this is the most distant thing we know of in the universe at the moment. It's being seen about 290 million years after the Big Bang. That's about 13.5 billion years in the past. Pretty remarkable. It's the little red piece of that thing. The little pink piece is something else. There are objects that are probably even further back that have been claimed, but we haven't verified. So this is the most distant verified thing with James Webb. So this is really remarkable. This is going to be for the next 10 years, astronomers are going to be studying these things and understanding how the universe started. If you read in the news back in 23, this was in the newspapers a lot, there were all these stories. These are just some early James Webb images, these interesting things. There were all sorts of articles about crises. James Webb is breaking the universe. The Big Bang is wrong, all sorts of things like that. The problem was James Webb is seeing galaxies really soon after the Big Bang, and they appeared to be much bigger than we thought. There were more stars than we thought. That was in 2023. The good news is by 2025, we don't think that's the case. Astronomers figure things out. Part of it is because the light you're seeing in these images, which we assumed was stars, is not just stars. Turns out it's stars plus light from those black holes that are accreting material. And so, in fact, we can see that. This image here shows you a bunch of black holes. These bright little points here are very, very distant black holes in the universe that are being lit up. And so we now think, when we're seeing these James Webb images, you're seeing stars plus the light being emitted from around the black hole. And so we think that the models actually are pretty good now, what they were. But clearly, this is something we got a whole bunch of stuff. Oh, you get in a transcript of my talk. That's pretty cool. Anyhow, so things appear to be pretty good, but still very interesting. What was I going to say about this? But this leads to another problem, which is why are there big black holes so soon in the Big Bang? Because these black holes also appear to be 1 million to 1 billion times the mass of the sun. How did they form just a couple 100 million years after the Big Bang? That's another mystery. So you just solve one problem with another, maybe. Okay, well, let's go back to the expanding universe, Hubble's other result. So this is Hubble's original diagram. We call it Hubble. This is the Hubble diagram, in fact. This plot on the scale he went out in distance is basically just a tiny little point on this plot. That's the modern plot. So we can now do these measurements much, much further out, as I've just showed you, a very distant universe. And of course, this is a big field of study. We're measuring the expansion rate of the universe to very, very distant parts of the universe. And when you do this result's now up 25 years old, but what you find is that the universe is not expanding at a steady rate in time. And in fact, the universe is actually accelerating. It's actually going faster now than it did in the past. You can see the plot here. If it was going at the steady rate, it would go along a straight line, but you see that that's the red line here on the left. You can see that most of the data points are above that line. This means in the past, the universe was slower than it is today. This is pretty remarkable. This, of course, also won a Nobel Prize for 3 astronomers. The universe is accelerating. Not only is it expanding, it's actually expanding at a faster rate in time. And this is due, we think, to a mysterious force called the dark energy. When you don't know what it is, you call it dark something. And this one's even more mysterious than the dark matter. We've only had 30 years to study this one. But the dark energy is, in fact, the dominant energy and mass component in the universe. It's about 70% of the universe, in fact. Something like that, yep. And so we think this is some force that's expanding accelerating the universe. Now, the dark energy has kind of two possible solutions. One is called the cosmological constant. And this is an interesting idea. This is just that space itself naturally has some dark energy attached to it. And so as you go out in time, the dark energy will be the same kind of as you go out in space. The other option is a model called quintessence, which is basically an energy that can change in time. It's a little more complicated. And what I'd say is that the cosmological constant has been the favored model for the last 30 years because it's simple. You just assume space has some dark energy attached to it, and we don't know why, but it's there. And in fact, going back to Einstein, when Einstein, he put a constant in his equations to make the universe not expand, to make it static. And that is effectively a cosmological constant. That's why he was kind of right, for the wrong reasons, but he was kind of right. But this is super interesting. Recent results from a very big study. There was, in fact, an update last week from this, from what's called the Dark Energy Spectroscopic Instrument, DESI, is suggesting, in fact, that that's not the case, that the dark energy appears to actually be changing in time. It's inconsistent with the cosmological constant, which means it does appear to be changing in time, which gives us all sorts of interesting conclusions, potentially. These are the possible future fates of our universe. Our current universe is expanding and accelerating. It's possible if this dark energy changes direction somehow. Right now, it's pushing away from, it's kind of anti-gravity, but at some point it could turn around and come the other direction, and we could expand and come back to a big crunch. I've always liked the big crunch. That's kind of fun. You could imagine it just keeps going back in some oscillating thing. The cosmological constant, which now seems unfavored, at least recently, suggests the universe will just kind of keep expanding kind of forever. Or you could have what's called the big rip. If the dark energy gets stronger in time, it just really, that's kind of violent and unpleasant. But if you believe these recent results, it's likely one of these two things, maybe, and not so much this cosmological constant. So this is, all of a sudden, I thought this was a pretty boring field. This is the thing that happens in astronomy. You think it's boring, and then before you know it, it's exciting again. This is pretty exciting. I would have thought 30 years ago, it's a constant, it's fine. This is pretty exciting. We don't really know where the universe is going to end up. We'll find out soon, hopefully. Or maybe not. We won't. Well, we'll know. One more thing about cosmology, I should say. So Edwin Hubble, there's a thing called the Hubble constant, which is how fast the universe is expanding today. And that measurement can be done the way Hubble did it, initially using these variable stars. And very famous astronomer, a previous director at observatories, Wendy Friedman, you hear about her a lot, has also done this measurement. And if you do this measurement, which is called the local distant ladder, you get a measurement. That's the red points there. But you can also get this number by studying the remnant radiation from the Big Bang called the because the error bars are small enough from both that they better overlap, but they don't. So you can see this. So this and this, the error bars are small enough that they're not overlapping. This means two different things. The measurements are done two different ways in two different parts of the universe, which suggests, if this is real, that there's some piece of physics we don't understand. So you read about this in the paper all the time. There was an article about this last week. I don't know. I haven't believed this for a long time. I thought, oh, somebody's making a mistake, but it's starting to become a little worrying that many years later, after like 5 years of this going on, that these two things are not converging. And so it could be that there's yet another mystery of the universe that we don't understand. So we don't know what the dark matter is. We don't know what the dark energy is. And we may not even understand some basic physics beyond that. So there's a lot of astronomy left to be done. Okay, So what's next? Let me talk about a few things. We have some great telescopes coming. The first one is the Vera Rubin Observatory in Chile. This is a recent image of it. This one's coming online this year. It's super exciting. It's obviously named after Vera Rubin, who was right here and did her work here. I'll show you why that was an appropriate reason to name her, named after her in a second. This telescope, it's not a very big telescope. It's the size of a lot of our other telescopes we have at the moment. But what's special about it, it has the biggest camera ever built. And so this camera and telescope will image the sky every 3 days. It will image the entire southern sky. Now that may not sound like a lot, but that's a huge accomplishment. I think people often think, oh, you've seen everything and the sky is really, really big. And our telescopes see very tiny portions of it. To image the entire southern sky every 3 days is a huge accomplishment. And the reason it's doing this is for several reasons. One is to look for things that move, or change in brightness or change at all. We call these things transients. So there's various different kinds of transients. This is just a little movie that shows you see how some stars are popping in and out. These are what we call variable stars. They're just changing in brightness in time. They're okay. They're not so exciting. The real exciting ones are the explosive things, like for instance, supernova, stars that blow up, or neutron-neutron star mergers and things like that. And so you see on the right here, you see there wasn't a star and then there is a star. And this telescope, because it's going to be imaging the sky every 3 days, is expected to find about 10 million of these events a night. That's a lot, yes. If you go back 30 years, we found maybe 50 supernova a year. Now we're going to find 10 million a night. It's incredible. This is one of the things the telescope will do. The second thing is because it's also imaging, you can find moving things. And that's going to be super interesting, I imagine, to Scott Shepard. This is images from Scott Shepard, who works here. This is a far out, which is a minor planet. I think probably the second most distant, because I think there's a far out now, right? But you see this image, you see two different images taken and the object has moved slightly. This is how you find things in our solar system. And this telescope will be really great for that. It's going to find, as it says here, 10 to 100 times more objects than we know about in the solar system. Basically, it's going to find all the space rocks, the smaller asteroids for the most part. This is going to be real exciting. But the real reason it's named after Vera is because it's going to be a dark matter machine. And the reason it's going to be a dark matter machine is because by imaging the sky every 3 days over 10 years, that's the project, if you stack all those images together, you're going to get very, very, very deep images of the sky. And this will allow us to look for very faint things, particularly allowing us to look for what we call dwarf galaxies, small galaxies, around the Milky Way. This is a simulation of what we think the Milky Way would look like, the dark matter halo of the Milky Way. So imagine the Milky Way is in there. We think, based on these curves that I showed you from Vera Rubin and others, that the Milky Way is surrounded by a whole bunch of little halos of dark matter. And so what you see in the simulation, all these little blue things are really little bits of dark matter. They're not little, they're millions to a little more than 1 million times the mass of the sun. A lot of those will be associated with a few stars. And with Vera Rubin, with these very deep images, we may be able to actually see those dwarf galaxies in great numbers. So this telescope will be a great way of studying that dark matter and asking, is this the right actual model? Is this the right model for dark matter? So that would be very exciting coming from Vera Rubin. There's also the Nancy Grace Roman Space Telescope. This is a small telescope. It's the same size as the Hubble Space Telescope. But once again, it's focused on a wide field. And this shows you that. This shows you the field of that telescope versus the field of the Hubble Space Telescope. And so you may be surprised to know in 35 years, Hubble has imaged less than 1% of the entire sky. Once again, the sky is very, very big. This telescope will allow us over its lifetime to probably image about half the sky at the beautiful resolution of Hubble. So that's going to be really quite remarkable. And this will be launched in just a couple of years. So this will be a very exciting telescope. And then we have the big ground-based telescopes, which we've been working on at Carnegie, among other places. There are 3 giant telescopes being built. One is, and they're very appropriately named and cleverly named, the European Extremely Large Telescope, which is being built by Europe and is extremely large. The Giant Magellan Telescope is giant because our current telescopes are called Magellan. So this is a giant version of that. And that's our one that we're designing at Carnegie in Chile. This is on our site. And the 30-meter telescope, which is being built by Caltech and UC and external partners. So these telescopes are just incredibly huge telescopes. And big telescopes allow you to collect light and see faint things you can't see otherwise. And because the bigger a mirror is, or the bigger the area of the mirror, the sharper the images. So they actually get better images than even Hubble and James Webb once you correct for the atmosphere. So just to give you an idea of that, this shows you a comparison of the James Webb image telescope mirrors compared to the Giant Magellan Telescope. So James Webb is a great telescope. I've just shown you some amazing images, but the GMT is going to just blow it out of the water. And in fact, this is the telescopes like this will allow us to, for instance, see Earth-like planets, which we really don't see the real Earth-like planets yet. You need a giant telescope like this to do that. And so that's really one of the primary drivers for this. But it also will allow us to study those very, very early universe galaxies I showed you in detail. So let me show you again. As I said, the bigger the telescope, the sharper the images. This is a field with Hubble. This is that field with James Webb. So once again, it's much bigger telescope. You see how much sharper it is. And this is a simulation of what it'll look like with the GMT. So you can just see how much sharper the images will be. Just really, really incredible. And then this is just another example. This is kind of a fake, these are all fake examples because this telescope doesn't exist. But this is a nearby galaxy, Whirlpool again, which I've now put at the very, very high redshifts I showed you in those deep Hubble images. And this is what those would look like with our Hubble Space Telescope today. And this is what it'll look like with the GMT. And so once you see the sharpness, you see the ability to actually, I don't know if I can go, I can go back. See, trying to understand that versus this, you can just see how much more detail we have in our ability. We'll be able to study the very distant galaxies the way we study the very nearby ones. Really incredible. And the other advantage, as I said, is a big telescope collects more light, so you can do things much faster and deeper. So this is just comparing James Webb. Sorry, this is a James Webb to a Gemini. This is not what I thought it was. That's mislabeled, sorry. This is the wrong, I put the wrong figure in, so I won't talk about that. So that's the good news. These telescopes are impressive. The bad news is they might never be built. And that's because even though we've invested huge amounts of money in these telescopes, each of these two US telescopes has raised billions of dollars between them from private parties. In the case of our telescope, we have Carnegie, but many other partners, Harvard, University of Chicago, Arizona, Texas A&M, many countries, South Korea, Brazil, Australia, big collaborations here. And similarly with the 30-meter telescope out of Hawaii. But the problem is these telescopes, these are expensive things. These are several billion-dollar telescopes. And really, we can't build these things without some investment from federal governments. In fact, Australia, South Korea, Brazil, those countries have participating from their federal countries. And of course, so we've been waiting for quite a while for the federal government to help here. This was ranked #1 by the astronomy community as our top priority for this decade. It's gotten positive reviews and everything, but we just have not been able to get the flow through of the money yet. And given the current situation, it's not looking particularly good, I must say. This would be really quite sad because unfortunately the Europeans will be building their telescope. And now we hear China is also building a large telescope in China. So unfortunately, the future of American astronomy really could be quite in the balance if these telescopes don't get built. So that's kind of the sad news, unfortunately. So we're spending a lot of time lobbying about this, but this is going to be quite challenging. So let me try to end on a more positive note than that. Maybe I think what hopefully you've learned from this is that, we've really in the last 100 years, we've learned a lot about the universe since the time of Edwin Hubble. And what I always say, this is one thing I will say about the big telescopes. Anytime you build a new telescope, I can tell you all the things I think it'll do. The most interesting things it'll do are the things we have no idea about. And that's the real reason. The universe always has surprises for us. And that's why you always want to build bigger and better telescopes, because there's some surprises we will just never know about. And I'll end there. Thanks. Oh, do I have one more?
Okay, we'll open the questions.
What is the definition of an Earth-like object?
Yeah, well, you're asking the wrong guy. We have real experts in this thing. So I should say there are planets the size of Earth that have been found. What I really mean is a planet like Earth around a sun-like star. So I guess the question is, what do you want to find? So we do see Earth-like planets around much smaller stars than the sun. That's just because they're easier to find around those small planets. But if you wanted to find, if you thought that, for instance, we're in a special system where the sun is the right kind of star for life or something of that sort, we can't find planets the size of the Earth around stars as big as the sun right now. I guess the other thing I'll say is to really, and this is another area where there's a lot of expertise on this particular campus. One of the most exciting things we're doing is being able to study the atmospheres of exoplanets. You probably have heard many talks here from that, I would hope, because people here are working on that quite a bit. And generally, it's very challenging to do that, except for the very, very biggest planets now, things much bigger than Jupiter in general. And these big telescopes will allow us to look at the smaller rocky planets, which are more interesting. Ultimately, if you want to ask the question, is there life in the universe? I think you need the big telescopes to get to those kind of rocky Earth-like planets.
What happens if stuff enters a black hole?
Sorry, what's that? It's gone. It's just ripped apart. Yeah, you don't want to find out. Yes. Do you want more details than that? That's pretty much the details I can give you.
So with the increase in the amount of data that you're getting from these telescopes, are you using AI
It's a-
to be able to do pattern recognition and that kind of thing? Has that increased? Maybe talk about that a little bit.
Yeah, it's a great question. Well, the answer is I'm not using that because I'm old, but you probably. But what we're finding, I think, is that the community is starting to warm up to this. What I found, at least for the astronomers we have in Pasadena, is that many of our postdocs, of course, are very, very aware of AI, and they're coming in with that skill set. I personally, this is something we talk quite a bit about. I would love to see Carnegie have a bigger effort in this because I think it will impact all of our science. But what we probably need are people who have some real expertise in that to interact with the scientists. Like someone like Mike or myself are never going to, unless we go back to school and start all over, have the details. But having people around who have that expertise and who we could work with would be super helpful, just as we have expertise building instruments. So we have people, Vera Rubin had Kent Ford, right? She knew what she wanted to do. She could go talk to Kent, build my instrument, help me build the instrument I need. I think AI could be like that for us here. But so this is one of my goals as president, is to see more of that here. Oh, I don't think it's on. Is it?
Yes.
There it's on.
I don't know if it's possible for you to give a quick answer on this, but I was just curious as to, you mentioned that dark clusters of dark matter would be associated with dwarf galaxies, and that would be one of the things that we'd be finding
Yes.
in your instruments. Can you explain a little bit what the association is between a dark matter cluster and a dwarf galaxy and why that happens?
Yes. So, so the dark matter is the dominant thing. All galaxies, basically, if we didn't have the dark matter, even galaxies, the regular galaxies probably wouldn't form. The dark matter is the dominant component that starts the gravity that basically pushes everything into them. So the idea is if you have enough dark matter, you should also pull in enough baryons, the regular matter that we're made of, to start star formation. The question is, but they're going to be really, really small systems. I should say, we know about some of these dwarf galaxies. It's just the Rubin Observatory is going to allow us to probably find many. The models predict that there should be hundreds potentially of these dwarf galaxies, and we know of, I have to go back and see the numbers, I don't know, tens of, as opposed to the hundreds that you expect. But the answer is the dark matter is what drives the star formation. If you have enough matter, you'll pull in the stuff that forms the stars.
You showed a simulation of two galaxies interacting. Are you modeling energy loss between the two galaxies? I would have expected them to just free fly on through with enough energy, but they came back through. So it struck me as you had some sort of energy losses.
Yeah. So in those simulations are exceptionally simple, and they're dominated primarily just by gravity in them. But gravity will dominate over those scales. Over any of the other forces. Gravity usually wins in these cases. Now, that's a pretty old simulation. That's 11 or 12 years old now. The new, more modern ones actually have real gas physics. There's like no gas physics or anything in that one. You're right, that's what has to happen. The newer, more modern simulations do all of that. They put in star formation. They even put in energy from these black holes potentially, because the black holes also, the material that's swirling around the black holes sends out material that also could potentially, blow up a galaxy the other direction. So all that stuff is in there, but gravity dominates by far. So, yeah.
Hi. What can you say about matter itself? In other words, why, for example, would the black holes, the dark energy, or the dark matter just eventually consume matter? There's no future.
Yeah, that's an interesting question. Well, that's even more dismal than my telescope part. Yeah, so let me just talk about the black holes first, because this is the common misconception about black holes. I think when I talk about black holes, people are like, well, why are we all not swirling into the black hole? Actually, that I'm surprised somebody always asks me, when I showed that simulation of the Milky Way black hole with the stars, people are like, why are the stars not falling into the black hole, right? Well, first of all, it's not as close as it looks because we're pretty far away. But the reality is, with a black hole, the gravity is very, very strong around the black hole. But once you get a little bit of ways away from it, it's almost like a normal gravitational object. So in fact, if you replace the sun with a small black hole, we would continue to orbit it. And so the strong effects from the black hole are really, you have to be pretty close to the black hole. So in terms of everything like getting sucked into it, you don't have to really worry so much about that. Because that's one of the most common questions I get, particularly kids, of course, are very interested in that. Well, the dark matter is flying through you right now. I mean, that's the thing. It doesn't interact with any of normal material. And so presumably it's everywhere. We don't know what it is, though, is the challenge. So the preferred models for the dark matter is some subatomic particle that we don't understand. Now, I'm going to get in. We're videotaping this, right? This is online. I better be careful what I say. I'm going to really get myself fired very fast for my job. One has to worry a little bit. I'm going to say, how do I say this? We've been looking for dark matter for quite a long time. And if you were to ask me, what is the one thing that we might have fundamentally wrong? I'm not saying it's dark matter, but it could be, right? Because you have to worry after, it's literally 1970, so that's a long time. It's almost, I was born in 67, so it's 55 years or something, right? Yeah. I can do math. Almost. After 55 years, we see evidence for dark matter in all sorts of scales. As Mike mentioned, I did this in the 90s. We see it at all different scales in astronomy, right? So astronomers have characterized the need for dark matter pretty well. And we've eliminated most of the potential candidates for dark matter. So you could have gone way back, and if you went back to the 70s and 80s, maybe it was planets or something. There were all sorts of astronomical objects that could have been the dark matter. We've eliminated pretty much all of those. We really are down to primarily some subatomic particle. But there's a whole bunch of experiments that are happening in physics space to look for those particles, and they're coming up empty as well. And so one has to at some point be a little worried about that, I would just say. It doesn't mean it's wrong. And right now I'm not saying it's wrong wherever on YouTube, so I want to make sure I'm just be careful. But there have been times where people were wrong, right? I mean, as I said, until 1918, we thought we were the center of the Milky Way galaxy, and we thought that was the whole universe. So I do think one has to be a little careful there. So I'm a little concerned about that for that reason. I mean, it's a long time we've been looking and haven't found it. So maybe there's something we're missing. We can edit that part out, right? I can't say that. There's too many astronomers in the room. I have to be careful what I say.
Part of a separate subject, big jump. Oh, okay.
That's probably good. Please.
Well, I think your point about dark matter is interesting, and who knows, it may be right, maybe the same for dark energy. But there's supposedly, and I thought it was the Vera Rubin telescope that's coming online very soon, that will look at the polarization from the cosmic background radiation. And apparently, and I don't understand it, I've just been reading a little bit about it. Apparently the polarization, once we know more about the polarization from the cosmic background radiation, it may say a lot more about which models for the Big Bang work. And that must not be the Vera Rubin. No.
That's probably, I think that has got to be one of the, because that's measured in millimeter wave and smaller wavelengths. So that is probably one of the South Pole telescopes or one of those. That's way out of my field of expertise now. But there are other telescopes that are being built to study that. I mean, you learn a lot from that. The cosmic microwave background is the remnant radiation from the Big Bang. We've learned quite a bit about it. I'm going to say something and once again get myself in trouble. You have to model it, though. They're modeling the data, and they have to make all sorts of corrections. You have to be worried about these things. I'm really going to get myself in trouble. We know what we're doing as scientists, but there's always assumptions in that. So even with that, that was one of my worries when I mentioned the Hubble constant, right? So the Hubble constant is measured two different ways. One is measuring the cosmic microwave background and modeling that. The other is using these Cepheid variable stars and supernova, which is like what Wendy Friedman and others do. And you can find many reasons why each of them could be there could be something that's wrong that we just don't understand. There's nothing wrong with that, right? All the papers I wrote in the 90s are definitely wrong. Definitely. That's right. And somebody once told me that's very depressing because you live and die and your career was useless. I'm like, it's not useless because because it's progress, it's just very slow progress, right? And over each of our careers, we make some progress, and then somebody else will pick it up, and somebody else will pick it up, and yeah. But yeah. So I don't know. So, but you're right. There are more experiments. That's why there's so much energy be put into that field, because you do learn a lot from that, from the cosmic microwave background.
Is the cosmological constant a thing, or it comes and goes, or is it a rationalization?
Well, it appears not to be right if we believe the current data. The idea is that it would be some parameter attached, like space itself would have some energy built into it, is the way to think about it.
The origin of that energy.
Well, that would nobody, I don't know if anybody knows. I mean, I do think there's a lot of theories. If you actually look up for the dark energy, there's like 200 different, it's all theoretical at this point. I mean, I think the reality is we're still just trying to parameterize it. And that's the thing. The dark matter, going back to dark matter, we've been studying for a long time. I think we've done almost everything we can do. Not exactly. There's still something. This Milky Way stuff is really interesting. The halo of the Milky Way. That's the last kind of thing that for astronomers, I think, really to nail down the dark matter. But the dark energy is still very new. I just think we know so little about it. I wouldn't lose sleep over it just yet. I wouldn't, but no. Anything else?
Okay, any other questions?
Oh, there's one in the back.
Yeah, so you mentioned that the Giant Magellan Telescope might not be built, but because you convinced all of us in this room to be excellent and excited fans of astronomy who want it to be built.
Yes.
What can we do to make sure it's built?
Yeah, that's a really great question. Well, I think it needs advocacy, obviously. So we spend a lot of time doing that, as you know. I mean, advocating right now, we're putting a lot of energy advocating, particularly in Congress. I think actually what we need is NSF would be happy to do the GMT and TMT. The problem is they need the money, and the money comes from Congress. And so I should say the GMT has partners in red states and blue states, which is super helpful. So we do have Republican and Democratic senators interested in the telescope. The problem is it has to be, we got to get them interested enough that they actually do something with it. And there's a lot of priorities. Obviously right now there's a lot of noise and a lot of stuff is going on. So I think this is maybe not the moment to push it too much, but we also don't want to wait too long, because the longer we wait, the longer it costs more money as you wait for this. But advocacy, science is important. I'll just more generally step back and just say basic research, which is what we do at Carnegie, is a great investment in the US economy. For every dollar we spend, we make $3 back or something. There's all these statistics. Where is Steve? Where is he? Sorry, where is he? He's back there somewhere. Maybe he left. He can tell you all the statistics. This is a really important thing that I think we haven't given that message out maybe enough, clearly, because clearly that message hasn't gotten through. You're all here, so you obviously think science is interesting and important. But I think we have to do a better job of advertising that more widely.
Maybe you can pass the hat around.
Yes. Yes. That's right. Yes. We will take anything. That's right. Thank you, Michelle. Yes. But thank you, everybody. Yes. Thank you.
Next time. Oh, I should remember
When?
to announce that the Hadley lecture will be held at.
The National Archives on April 9th.
Thank you.
With Dr. David Charbonneau, the Cobley Prize winner of astrophysics in 2021.
What time?
6:30.
One of the world's experts on exoplanets.
World expert.
Thank you, everyone.
Awesome. Oh, good. Of course.